All right, guys, we're almost there. I'm almost done discussing this stuff, which is good because tomorrow they don't want anybody out and about. Do what you got to do, guys. Look at the stuff as best you can. We're doing it, and let's get through it. Let's just get through this stuff. This should go pretty smooth. 14 should not be too bad as far as the stuff I'm asking you to kind of have under control and know how to do this stuff. You've got all of the notes, guys. I do have the Doppler effect derived. I derived it in a way that I thought was better. That's me, but that's just my personal taste on the whole matter. It's a little different than what I've seen in other places, or perhaps I wasn't reading it right in other places. But the way I derived it, I liked it a little bit better. So if you want to see a derivation of the Doppler effect, you can see it in most of the basic physics textbooks, and you can see me having done it as well. Maybe it's more straightforward for you. However, maybe it's not. For me, it's more straightforward because it's my derivation. I was kind of looking at my particular way of looking at it. But as we look at this, for topic 14, let's kind of have it in mind what it is that we're looking to do here. One thing that's really standing all over the place on this thing is, now I'm not entirely crazy about the way the book does. I don't like the way they do everything. I like some things, but not everything. Let's kind of look at the Doppler effect in some sense here, guys. The Doppler effect says, and I'm not going with the book's way of doing it. I'm doing kind of my way here. FO, or at least what other books do. The frequency that the observer observes, the frequency that the observer encounters, equals the frequency of the source times the speed of sound. So different, like I said, different books write different things here, guys. Speed of sound plus or minus the velocity of the observer over the speed of sound minus plus the velocity of the source. What's going on here? FO, and you'll see that in my derivation, I'm relatively faithful to this notation right here, and I've seen this in other books, in my derivation of the Doppler effect. So you might want to look at that. You don't need to lose a whole lot of sleep on it, because I'm not going to ask you to derive anything on an exam, but it's fair game maybe in some other circumstance, maybe on a homework assignment or something, or who's to say. But it's just good to know some of this stuff. So use your best judgment on this, you guys. As we look at this right here, I'm doing it different than the book. I'm making all velocities, I'm making all magnitudes positive, which means what? The frequency that you observe, is equal to the frequency of the source times this ratio. Now what does this ratio mean? This is the velocity of sound in that medium. If you go plus, you are coming at the observer. The observer is actually running towards the source. So when you look at this, you got this and you got this, guys, right? So as we look at it, if you're going plus VO, I don't make any minuses, any negative signs here. The way to do what other people do is they want you to kind of put negative numbers in there. All my numbers are positive. FO is the frequency you observe, FS is the frequency of the source, V is the speed of sound, V is the speed of sound. VO is the speed of the observer, VS is the speed of the source. If the observer is running toward the source, then you use plus on top, because it's going to feel, the observer is going to feel like the frequency is more frequent. He's going to run right into the wave. So you use a plus right here. If you're running away from the source, you use a minus. If the source is, if for some reason, if the source is coming at you, then you use a minus here, because a smaller number on the bottom makes a bigger frequency. If the source is coming at you, you're going to feel like you're experiencing the frequency much more frequently, so to speak. There's going to be a greater frequency if he's coming at you. Why is that? Because V minus VS is a small number. What's a small number doing division, you guys? A small number doing division gives you a big answer. So if he's coming at you, it's minus on the bottom. If the source is coming at you, it's minus on the bottom. If the source is running away from you, it's plus on the bottom. Here, if you're running toward the source, it's plus on top, minus on top if you're running away from the source. Here, if the source is coming at you, it's minus. Kind of the opposite of what's going on here. It's minus. But if the source is running away from you, it's plus. That's why they write it like this, guys. That's why you see this in this particular fashion. Christian, that's the plus and the minus are pretty obvious. I didn't make them I didn't warp them too much or anything, did I? Okay. So there they are. That's kind of the thing that's going to run the show here. So if that's what's going on, let's make it happen. And there's other things we can put on there. And there's like I said, there is a good amount of, there's some stuff I'm just not going to kind of test you on as hard as other things. And you kind of see that, you kind of look at it with the exams you're going to see, and definitely going to see with the homework assignments. But if you look at page 487 and 488, page 487 and 488, they summarize pretty good, some pretty good stuff there to look at. All right, let's get the show on the road, guys. 29, 30, and 31. Here we go. For 29, topic 14. For 29, two trains on separate tracks move toward each other. Train 1 has a speed of 130 kilometers per hour. Train 2, a speed of 90 kilometers per hour. Train 2 blows its horn, emitting a frequency of 500 hertz. What is the frequency heard by the engineer on train 1? Now they're both coming at each other, but only one of them is the source. Why? Because only one of them blew their horn. The guy who blew the horn was in the slower train. Train 2 blows its horn, and it emits a frequency of 500 hertz. What is the frequency heard by the engineer on train 1? All right, so there's a lot to do here, guys. Let's make it work. For 29, and again, guys, this is big. They say it a little differently in the book. If you're more comfortable with the book, follow the book. This is the same thing as the book, but I use it this way. I just think it's a little more of a gut feeling as to what you need to see. But that's your choice. That's your choice. It's your personal taste on how to approach this whole matter. V1 is 130 kilometers per hour. What does that mean? Well, I know it means one thing. We want meters per second. 130 kilometers, each kilometer is 1,000 meters. Here's 1,000 meters for you. An hour is 3,600 seconds. 3,600 seconds. V1 for train 1, 130,000 meters divided by 3,600 seconds, you got 36.11 meters per second. We got it. We got that. How about V2? Let's go to V2. V2 is saying that guy's going a little bit, not going as fast, going 90 kilometers per hour. 90 kilometers is 90,000 meters per hour. An hour's got 3,600 seconds. Okay, you guys know this. Kind of cutting to the chase a little bit every time I'm doing this part of it. Get the job done. You do this, all right, we got that one. I tell you what, you got to remember now, this guy's the guy who sounded the horn. Train 2 sounded the horn, so he's VS. He's the source moving. Train 1 is going to be observing it. So he's the V0 guy. There it is, way over there to the far left, you guys. That's where this whole thing's going to play. That's where the whole thing's going to play out. So you look at it, and you say, FO is going to be FS over Well, okay. Yeah, it looks familiar. We just did it. I was jumping up and down about that earlier. Now, which one are we going to use? They're both coming right at each other. They're both coming right at each other. What does that mean? Well, it means exactly what I just said. I mean, if they're coming at each other like that, you guys, let me get... If VS is coming at the other one, it's a minus. Why? Because it's accentuating the amount of frequency that is going to be experienced. He's coming right at the observer. Yeah, I know. I got more news for you. The observer's coming right at him. Wow. Big number divided by small number is going to be a big answer. Yeah, that makes sense. That makes sense. FO. I don't know what it is. 5 times 10 to the 2. It's a fancy way for saying 500. Why don't you say 500? They're trying to throw you a little bit. 340. 343 meters per second is the speed of sound. The fast guy coming right at him, the observer, is 36.11. The slow guy, minus 25. The rest is math. Round out the answer. You know it's going to be, this is definitely bigger than 1. It's going to be something bigger than 1 times 500 is going to be more than 500. There it is. That's 29. All right, let's go to 30. 30 is saying, at rest, a car's horn sounds the note A, which is 440 hertz. The horn is sounded while the car is moving down the street. At rest, it sounds the A note, right? Which is 440 hertz. At rest. The horn is sounded while the car is moving down the street. A bicyclist moving in the same direction as the car. So the car's catching up to him, and hopefully the bicyclist is, exercising. Hopefully everybody in this situation is exercising good ethics on that, right? Good etiquette, I guess you could say. The bicyclist is on the side of the road. He's safe. The car driver is not looking at his cell phone, and they're getting the job done, right? A bicyclist moving in the same direction with the car catching up to him. He's moving 1/3 the car's speed. The bicyclist is moving 1/3 the car's speed, and he hears a frequency of 415 hertz. Interesting. If the cyclist ahead is the cyclist ahead of or behind the car, what is the speed of the car? That's a great question. Very good question. What was this one? That was 31, right? Yeah. 30, right? What's going on here? Again, I guess I jumped the gun too. I mean, for all we know, the car's not going to endanger the bicyclist because the bicyclist is behind him, right? The bicyclist might be riding behind him, and the driver's just going right ahead. So we don't know who's who. We do know the car. We do know that the frequency of the horn. I know a couple stuff here. They said this thing about an A note and everything else. The frequency of the source is 440 hertz. That's in a still situation. That's when nobody's moving. The frequency of the source is 440 hertz if the car is at rest. The bicyclist hears let's see what we got here now, guys. Let me think. So we don't know exactly what's going on here. We know that both people are on the road. Both people are driving safely. Both people are very careful not to create any problems for anybody. The whole thing. We got all that under control. They're both on the road. The bicyclist is somewhere. The car driver is somewhere. They're both in a safe place. They're both driving. The car, when driving, is going at a velocity. Well, he's the source, I guess, right? We'll say he's going at a velocity or magnitude of velocity, Vs. The bicyclist, he's the observer actually. He's going 1/3 Vs. It's that simple. So, Vs is just whatever the Vs is, you guys. So let's see what we got here. I'll tell you what. I guess there is a way to know where the guy is. And they're asking the question in a particular way. They're saying, is the cyclist ahead of or behind the car? What is the speed of the car? For A, that's not that bad. If the cyclist is hearing if the cyclist is hearing that kind of frequency, that means the car, I'm guessing this, how's it going to happen? If you're going to do this, if the observed 415 is obviously smaller than the source, 440, that means 415 divided by 440 is a ratio less than 1. For this ratio to be less than 1, and they're both going in the same direction, if the source was coming at the guy, and he's trying to run away from it. Let's just see where that actually goes. We could say that FO over FS is equal to 415 over 440. Correct? 5 goes into here 83 times. 5 goes into here 88 times. The ratio is 83 out of 88. So, that's got to be equal to something going on here. If the source is going toward the observer, you'd have this. And if the observer is running away from the source, you'd have this. If the car was behind the guy, if the car was behind the bicyclist, the bicyclist would be attempting to flee the source of the frequency, in a sense. I don't think there's not a movie where there's a chase scene or something, but he's basically running away from the source if he's ahead of the source. If the source is coming at him, we put a minus here. Do you understand this is a pretty big number, and this is a pretty small number? Big minus small. Big number minus small, big number divided by small number. Big number divided by small number is big number divided by, so this is going to be something big. Basically, this is more than V, this is less than V, this ratio is greater than 1, and that's not true. That ain't true. Well, let me go over here. The only other way it could happen, guys, is if I was the bicyclist, the observer, and I'm chasing the car, and the car is fleeing me. Christian, is that visible pretty good? Is it, the writing's okay? All right. So you see that? This is the way it's going to work. I feel like almost taking this thing off for the last problems, man. Yeah, I better not. All right. So essentially, this is what's making it, guys. The 415 over 440 reduces to this, and the only way you're going to get it to be an equation is if VO, VO is small, V's a constant, VO is small, V's a constant, VS is bigger than VO. VS is bigger than VO. So this is the denominator is bigger than the numerator. That's the only way it works. So what does that mean if that's the only way it works? If that's the only way it works, the bicyclist is behind the car. So behind the car means they are getting farther apart. They are being, they're getting farther. So I have that in the notes. Just you look at it as well. So for the whole process there. So bicyclist is behind the car for A. Okay. Now what are they asking? How fast is the bicyclist going? I mean, how fast is the source going, and how fast is the bicycle? They're just asking the source. If I know if the source is going 33 meters per second, and the bicyclist is going 1/3 the speed of the source, if the source is 33 meters per second, what's 1/3 of 33? It's 11. If one guy's going 33 meters per second, and the other one, the slower guy, is going 1/3 the speed, 1/3 of 33 is 11. 11 meters per second and 33 meters per second is what's going on. All right. They told us this. We just got to be careful. The observer is the slow guy. What does that mean? He's the bicyclist. The guy giving off the source is the car. If the bicyclist is 1/3 VS in terms of speed, the source is 3 times faster because the bicyclist is going 1/3 the speed of the source. And then this is what happens. So if that's the case, let's see what we could say about it to make it happen. So I am essentially saying that this guy made it happen right here. So let's go there. So what did we say here? We said we already drew the conclusion. The cyclist is behind. The cyclist is behind. The cyclist is behind and he's not as fast as the source. If the cyclist is behind, he's trying to catch the source. If the source is fleeing from him, that's also a positive right here. They told us that the cyclist is going 1/3 the speed of the source. Sounds good to me. Divide by FS on each side. Man, my hands hurt in places I thought I never had. All right. So we're almost there, guys. V plus or minus 1/3 VS. This is this. Sounds good. You are taking 415 over 440. You got 343 plus 1/3 VS. Christiana, is that visible pretty good for you on the camera? It's all right? Okay. This thing right here, you can factor a 5 out of here, factor a 5 out of there, and then cancel those 5s. And you got 83 343 plus 1/3 VS. Take a shot at it without it. We'll see what happens. Got that. The V is 343. 343 here. Cross multiply and make this thing happen. See where we are here. All right, we're not going to have to do a whole lot at this point. Once you get here, you're going to cross multiply. Guys, there's one equation here with one unknown. It's called VS. There's one equation with one unknown. That's it. Take the 88, multiply across. Take the 83, multiply across. Kick it around all sides, kick it around all kinds of ways you want to kick it around. And it's going to be 53.67 VS equals 1715. Divide by 53.67 on each side. The source is going 31.96 meters per second. If they want to get slick, they might want to ask you, well, how fast was the bicyclist going? I didn't ask how fast the source was going. Well, actually, they did ask how fast the source was going. But if they don't, how fast the bicyclist is going? 1/3 of this. He's going about 11. About 10.5 to 11 meters per second. 10.5 to 11 meters per second for that. Okay. That's 30. Let's do 31. and we're done. And that basically takes you through the course, man. This is stuff I want you to kind of pay attention to. I normally don't get this up front this fast. You know, I don't know if I ever have. We had the circumstances happen that happened, and this is what we got to do. Okay. So we did 29 and 30. Let's do 31, and we're done. All right, guys, let's finish this up. 31. An alert physics student stands beside the tracks as a train rolls slowly past. He notes that the frequency of the train whistle is 465 hertz when the train is approaching him, and 441 hertz when the train is receding from him. Using these frequencies, he calculates the speed of the train. What value does he find? It's a great problem. So, we know a bunch. And like I said, I erased something I didn't want to erase, but that's all right. We'll put it here again. Fs, V plus or minus V0 let's see what's going on here. Let's say the guy observes something when there's an approach. The observed frequency regarding the approach of the train is the following. It's the frequency of the train whistle when it's still, when it's not moving. Frequency of the train whistle when it's not moving, and I'm not moving. Let's say I'm the observer. I'm the observer, I'm 0, I'm not moving anywhere. When it's coming at me, it's V minus Vs on the bottom. When the source, the train's coming at you, it's that. When E is leaving, receding, whatever, when it leaves, recedes, I'm still not moving, and now that's a plus right here. So these two guys tell you something. What do they tell you? Well, I'll tell you one thing. He says there's a difference, isn't there? There's a whole lot we can say. What he observes. You could play this. You could definitely play this a number of ways. I think I'm going to play it the easier of the two ways here when it's saying this. One of them's, when he's coming at you, it's 465. When he's leaving, it's 441. 465 coming at you and 441 leaving you. Tell you what I'm going to do. Let's what value does he find regarding the speed of the train? Okay, I'll tell you what. What do you say we do a ratio? Approach frequency, receding frequency, or leaving frequency, whatever. The ratio of the two is the ratio of these two. Yeah, well, Fs and Fs cancel. Good, because they never told me what that frequency was. So Fs and Fs cancel. The Fs and Fs cancel. The V and the V cancel. And this guy flips up and goes over here. So if you look at it carefully, let's watch it again. Take the ratio of these two. Take this, and divide it by that. This divided by that is FO over FR. This divided by that is FOA divided by FOR. And that's the same as this divided by that. The FS's cancel, the top V is gone. Top V's are gone. That flips when you do the division, and you get to here. It's not bad. They're telling me it's 465 when it's coming at me. They said it's 465 when it's coming at me, 441 when it's leaving. 343 is this guy. I don't know the speed of the source, the speed of the train, and I just don't know it yet. But I got this. The rest is math. The rest is pretty straightforward math at that point. Said it was going pretty slow. When you look at it, So you got this, and you got this. And you're going to cross multiply and solve that equation. It's going to be that simple. When you do that, and I got it in the notes and stuff like that, it's going to come out to something like this. 906 VS equals 8232. VS equals 9.09 meters per second. Might as well make it dramatic since it's the last problem we're doing on this thing. And there it is. Stuff should be pretty straightforward, you guys. Here, again, there's a lot of song and dance you got to do to solve this, but it's not really difficult, but it is tedious. It's not conceptually difficult, but you're going to solve for V sub s. And you're going to get all the V sub s's over to one side, you're going to do the whole thing. I got a little more detail on it in the actual notes. This is it, guys. That's, let me write up what the problem was, actually. Just so we're agreed here. That was problem 31. All the best to you guys. It was great having you as a class. All the best to you. Stay safe, okay? Take care.